created by MindSticks Foundation Trust.
Hello, and a very warm welcome to today's explainer. Let's quickly look at our syllabus. First up, we're doing balancing equations. Next, I'll walk you through a step-by-step guide. Then we look at combination reactions, and we'll wrap things up with decomposition reactions. Let's get started, shall we? Section 1. Balancing equations, the law of conservation of mass. Right, before we start shifting chemical formulas around, we have to recall a golden rule. Atoms can't just magically appear out of thin air, and they absolutely cannot disappear. No magic here, they simply rearrange themselves. So, a balanced equation is simply one where the total mass and the exact number of atoms of each element in the reactants is perfectly equal to what you have in the products.
Moving on to Section 2, a step-by-step guide to actually solving the equation.
So, how do we actually do this on paper? Well, we use a bit of trial and error. Here are the 4 critical steps we are going to use to solve literally any chemical equation mystery. Step 1. Write the chemical equation out from the word equation. Step 2. Systematically check if it's balanced by counting up the atoms. Step 3. Start your balancing act with the compound that has the maximum number of atoms. It's just easier that way. And Step 4. Write down your beautiful, final balanced equation. Okay, let's put this into practice with our main example for today. Here we have a reaction between sodium hydroxide and sulfuric acid, and that gives us sodium sulfate and water. Written out, that's NaOH plus H2SO4 yields Na2SO4 plus H2O. Now, look closely at this. Tell me, does that look perfectly balanced to you at first glance?
Let's use this tally table as our scratch pad to be absolutely sure. If we count the atoms on the left, the reactants, and compare them to the right side, the products, we immediately see a bit of a problem. Look at the sodium. We have 1 sodium atom on the left, but 2 on the right. Oxygen has 5 on both sides, so that's perfectly fine. But then hydrogen has 3 on the left and 2 on the right. Sulfur is balanced at 1 and 1, so this table proves our sodium and hydrogen are definitely out of balance. We've got some work to do.
All right, jumping to step 3, we tackle the biggest compound first, sodium sulfate, Na2SO4. Let's balance those sodium atoms. Since there are 2 sodium atoms on the product side, we obviously need 2 on the reactant side. We fix this by simply placing a factor of 2 right in front of the sodium hydroxide, making it 2 NaOH. Now, please remember, and this is a mistake a lot of students make, we cannot change the actual chemical formula. We can't just write Na2OH. No way. We can only add numerical multipliers to the whole compound.
Now, what's really interesting here is that adjusting our sodium accidentally changed our hydrogen count on the left side. See that? We now have 4 hydrogen atoms in the reactants. To fix this, we have to look over at the product side again. If we apply a factor of 2 to the water molecule, making it 2H2O, boom! That gives us 4 hydrogen atoms on the right side as well. And the best part? We successfully equalize the hydrogen without messing up our oxygen count.
And just like that, we arrive at step 4. We can now confidently write down our final, perfectly balanced equation. 2 NaOH plus H2SO4 yields Na2SO4 plus 2 H2O. If you were to check our tally table now, I promise you, every single element is perfectly equal on both sides. This is a brilliant example of how our step-by-step trial and error method turns a messy, unbalanced equation into perfect chemical harmony. Okay, section 3, combination reactions. Coming together. Now that we've mastered the mathematics part, let's explore how these chemicals actually behave in the real world. Our first type is the combination reaction. The definition is beautifully simple. It's when 2 or more reactants combine in a reaction to form a single product. Really lock that phrase into your minds, single product. You might have multiple ingredients going in, but only one unified product comes out at the end. Let's walk through a few classic examples you'll see in your textbooks. When ammonia gas and hydrogen chloride gas meet, they combine to form solid ammonium chloride. If you did this in a lab, you'd actually see it as this dense white smoke. It's quite cool. Or think about burning a magnesium strip in the air. It reacts with oxygen to form a single white powder called magnesium oxide. Another super common one is mixing calcium oxide, also known as slaked lime, with water. This forms calcium hydroxide and releases a massive amount of heat. In all these cases, do you spot the pattern? The reactants are merging together to form just one single product. All right, section 4, Decomposition reactions breaking down.
So, we've just seen substances coming together as friends. Now, prepare yourselves for the exact opposite behavior. A decomposition reaction is defined as a reaction where there is only one reactant, but it gives rise to two or more products. Notice how this is literally the reverse logic of the combination reaction we just looked at? We start with a single, complex entity, and it just breaks apart into simpler pieces.
Take a look at this laboratory setup on your screen. We have powdered calcium carbonate being heated really strongly in a test tube over a burner. That intense heat essentially forces the single calcium carbonate reactant to decompose. It breaks down, leaving behind a solid calcium oxide powder while releasing carbon dioxide gas. That gas then travels right through the bent delivery tube and immediately turns the freshly prepared lime water in the second test tube milky. This is such a classic visual demonstration of decomposition happening right before your eyes. What is absolutely crucial to understand here is that decomposition almost always requires an input of energy to force that breakdown. For instance, if you apply heat to sugar, it divides into black carbon and water. Sometimes, though, the breakdown happens naturally over time, like how liquid hydrogen peroxide slowly decomposes into water and oxygen sitting in your medicine cabinet. Oh, and we can also use electrical energy. If we pass an electric current through acidulated water, it completely decomposes into hydrogen and oxygen gases. We call this specific process electrolysis, but whether it's heat, light, or electricity, energy is the key driver here.
Let's put the core differences side by side so you can easily memorize this contrast. In a combination reaction, multiple reactants form one product. Simple. But in a decomposition reaction, one reactant forms multiple products. You see? They are simply two sides of the exact same chemical coin.
As we bring today's explainer to a close, I want to leave you with a thought that connects our textbook chemistry to the real world. These degradation processes happen in nature all around us every single day. Think about microorganisms breaking down organic waste to form manure and biogas, which we then use as fuel. How does that natural, everyday process mirror the strict decomposition reactions we study today? Remember, science isn't just stuck in glass tubes in a laboratory. It is happening constantly in the environment all around you. Thank you so much for focusing and learning with me today. Keep observing the world, and I will see you in our next explainer.